I'm going to talk a little bit about the Knet machine learning framework that I've been developing for the last about 2 years. So first I'll try to start with some motivation on why people in deep learning should use Knet and or Julia. And then for those of you who missed the tutorial, the wonderful tutorial that Pontus gave yesterday, I'll try to summarize what machine learning is in about 5 slides. I also have some example models, but I'm going to skip most of them. How many of you actually attended the deep learning tutorial yesterday? So for the rest of you, the models are available, the example models are available online. So we'll look at a couple of them, and the rest of them you can see yourself, because I want to spend some more time on actually looking under the hood, how it works with the new type of GPU array that I prepared for Knet and the AutoGrad implementation. Okay, let's get started. So I want to start with a little Twitter conversation I had with a fellow AI researcher last week, Gregory Chupala. He was actually tired of using Theano, and he was asking people whether he should switch to PyTorch or Dynet. So whenever I see something like this, I'm like, dude, you know, what's up with Julia? So I've written this Knet thing, and it does, you know, has GPU support, does dynamic graphs, you can do VGG and RNNs at the same time, etc. So he says, sounds cool, but Julia? And then I very scientifically responded, Julia is awesome. And I know like the 140 characters of Twitter doesn't allow me to make my argument for why Julia is good, so you can consider the rest of my talk as a continuation of my response to Gregory. Okay. So let me start with why Knet is recommended. So Knet is a framework developed purely in Julia. It doesn't actually fall back on any external libraries. The only thing other than Julia is a bunch of CUDA libraries for GPU work. It's been actively developed and used by me, my collaborators, and students for the last 2 years. I use it in my deep learning graduate class. The final requirement for that class is actually to replicate a recently published archive paper on deep learning, which is not necessarily the easiest thing to do. So a third of the students usually drop before finishing, but quite a few of them actually, within a space of a semester, learn Julia, learn deep learning, and are able to replicate one sort of decent piece of work from recent publication. And I don't think that would have been possible if I was not using Julia as my language. And also, we've used it in a number of research publications. My research is on natural language processing, like Pontus, and I do some machine learning. And recently, we've been dealing with models that use vision and language together. So that means you have different types of networks actually merged within the same model with some attention mechanism, etc., that I think Julia makes really easy to express. One of the questions I get asked a lot is, how is your performance? So each row in this table is a different benchmark that we ran, comparing various major frameworks with Knet. And as you see, the numbers below Knet are neither the best nor the worst. They're usually fairly close to some of the other frameworks. Even though I'm doing AutoGrad and dynamic graphs I will explain later, it's still quite fast for practical purposes. The other thing I want to point out that TensorFlow is the slowest by far, and this is in spite of my students actually trying to optimize it for a couple of weeks. And so, you know, in spite of the hype, do not think that the most popular frameworks are always the easiest to use or the fastest for that matter. So what is Knet.jl? It's basically Julia. So when I first started developing it, I was actually following the Theano TensorFlow approach. I had a modeling mini language that I defined inside Julia. I wrote a compiler for it. and it would actually take the models written in this mini language and then convert it to a computational graph so that I could write the backprop, etc. So that's the static graph that Mike described in the previous talk. But then my students kept asking me, oh, but we want, for loops, and we want conditionals, we want this, we want that for more complicated models. And I'm not a compiler writer. So eventually I said, well, the nice Julia people already wrote all of this stuff for me. Why not take advantage of that? So just allow people to write their models in Julia itself instead of trying to invent a mini language that is actually poorly structured. So basically, Knet is Julia plus very little else from the user's perspective. This little else includes some GPU support and some autograd functionality. And behind the scenes, there's a bit more that has taken most of my time within the last year. Some efficiency improvements, memory management, convolution libraries, kernels, etc. But my goal always, at this point, my goal is basically to tell the user, just use Julia, write whatever model you want, and I'll take care of the rest behind the scenes. And why Julia? Well, there are a couple of reasons to prefer language: efficiency, expressivity. In terms of efficiency, I don't need to tell you guys the advantages of using Julia. When you're doing deep learning, most of the time you spend is actually outside of the deep learning model building and training. It's a lot of data manipulation and filtering and pre-processing, etc., for all of which Julia, I think, is a much better language than Python. And then once you start building your models and training them, also the low overheads you get with Julia are great advantage. Now, in terms of expressivity, I'm not a computer language person. Here's my cartoon evolution of computer languages. So basically, back in the Stone Age, people started writing things with machine code because they didn't have anything else. And then we invented assemblers to actually make it a little bit human readable. And then we had these terrible languages like BASIC and Fortran. Then we invented structured programming. And then ... eventually we got to Julia, right? So right now, the deep learning frameworks like TensorFlow are at the same level as the assembly languages of 1960s in terms of this. So this is sort of my analogous development for the deep learning languages. So in 2012, when CUDA ConvNet started writing kernels and programming everything else in C++, that was basically the machine code of the deep learning age. And then Caffe came up with this declarative language where you could actually list a bunch of operations and give the different options for each of the operations. That's exactly like what assembly language looks like. And then the other better frameworks like Torch, Theano, TensorFlow actually moved one step beyond that, but still they're missing various high-level language features because they want to be able to compile this computational graph statically. And most recently, maybe within the last year or two, people have been switching to this dynamic computational graph thing where the differences between analogous to static compilation versus interpretation. So in dynamic computational graph implementations, you let the user write the model in any language they want. You instrument that, and then you record all the primitive operations, and that gives you the computational graph automatically. You don't actually have to compile the language yourself. So as my final arrow indicates here, I see the future of the deep learning languages to converge to Julia as well. So we might as well actually start there. That's why the Knet philosophy is just Julia and little else. So for those of you who missed the tutorial yesterday, I'm going to teach you machine learning in 5 slides now. So at least this is the supervised machine learning. There's more different types, but the most common supervised machine learning type. You basically start with some observations. These observations consist of some inputs that go through some unknown process and that lead to some outputs. So you collect as many examples of these things as possible. And then to model the unknown process, you basically write a differentiable program. Okay? This differentiable program has some parameters, and if you twist the parameters, you're able to change the output of this model. This can be a neural network or any other thing for that matter. And you your program gives you, for the same inputs, certain predictions, and you want these predictions to be as close as possible to the real outputs you observed. So for that, you define a loss function. The loss function takes some, let's say, parameters for your model, the inputs x and the desired outputs y gold. It calls some sort of predict function to get y pred, and it returns some sort of measurement of how bad y pred is compared to y gold. So this is the quadratic loss function, for example. And then once we have the loss function, we basically write some sort of optimization loop. Typically in deep learning models, stochastic gradient descent is used. So I'm going to go over this code a little slowly. So W, the first parameter, is the parameters of the model, and they're typically initialized randomly. Data here in this way of writing the code is basically an array of tuples, and each tuple is an XY pair. They're training examples. Loss is actually a function that we saw in the last slide. It can be the quadratic loss or some other loss function that tells you how bad your predictions are. And then in the first line of the function, there's this interesting thing called grad. That's the only function that Knet adds to Julia, pretty much. It's a higher order function that takes a function and returns a function. In particular, it basically returns a function that computes the gradient of the parameters with respect to the loss. I'm going to talk about that in a little bit again. Inside the loop, we basically go through the XY pairs in data. We compute the gradient for each XY pair or mini batch, and then we move in the opposite direction of this gradient by some learning rate. So this is basically SGD in 5 lines of Julia. Now back to this grad function. What does the grad function do? Here is a bigger picture, so it actually makes sense. So normally, if you have a function f, we can actually think of this as taking some parameters w, some inputs w, and producing a value fw. If you use the grad higher order function to generate g, the gradient, the job of g is to take the exact same inputs as f, but instead of returning a value, instead it returns the gradient, which has the exact shape and size as w, but instead of, it's basically telling you for each entry of w how much the output will move if I move this input, an epsilon. Okay, so that's the gradient. So basically, a machine learning system helps a user do some of the things that can be automated. So it's still the programmer's responsibility to collect the data, determine what model to use, the parameters, the loss function, etc. You decide all that. But ideally, everything else should be done by the machine learning system, which basically helps you optimize the parameters using the gradient of the loss function. Okay, so some of these, the title or the subtitle of my talk is a, introduction to deep learning in 100 lines of Julia. So it's not exaggeration. In 100 lines, in these 5 examples, I actually implement linear regression, softmax regression, multi-layer perceptrons, convolutional networks, and recurrent networks. But I'm going to actually just skip over it, partly because they've been covered in other talks. I just want to show you one example. The example of convolutional neural networks. These are actually used to typically with images. So in this particular case, this demo, I'm using them to recognize digits. And typically what they look like is this picture. You have an input image. You apply a convolution operator to this input image, which gives you a stack of processed images or features. There's some subsampling operation called pooling, and you do this several times, and then you do the regular neural network, fully connected things several times. And that's typically the architecture that deep learning models that rainbow operators these days use. Except that they're much deeper than this. This is an old 1990s model called the Net. this code for 5 minutes, you basically know what it's doing. It's pretty close to the math. I can actually change and make this hundreds of layers if I want. Okay, I don't. Not only implements Knet, but for example, using the exact same code, I can implement BGG, which is one of the sources we want in this case. Contrast, I just want to show you the cafe implementation of the same model. Looks like this. Nice. Here's the TensorFlow implementation of the same. Again, you know, I don't want to go into details, but basically, I find that the Julia implementation is usually much more concise and easy to understand. So that's why I want to send the program. So, in the last part of the talk, I want to actually go a little bit into how this works. If we have time at the end, I can show you examples. Before doing that, to motivate why we need a language like Julia, I want to show you some of the more modern models that are being used right now. So this is actually a bidirectional LSTM. So you just saw LSTM in Mike's talk. Each of these dots is actually one of those LSTMs. So there's these LSTMs are traversed forward, one character at a time, just like Mike's talk, and then backward, one character at a time, and their outputs is actually fed to another layer of LSTM, which also go forward and backward, and this actually happens 5 times, and the outputs are actually given to a return decoder, which is also a non-trivial algorithm. And this model was used, for example, to tag name entities and state-of-the-art accuracy. Now, imagine having to write this model without using any for loops, any decent array operations, and having to actually construct the computational graph in your head. Okay, so that's very difficult. Whereas in Julia, if you have the LSTM primitive, this is fairly easy to write. Okay. Here's another example. This is from Google, just came out recently. It's called relational networks. They use this for visual question answer. So the idea is you're going to show the computer a picture and ask it a question, and the computer is going to basically look at the picture and find the answer to the question. So you see a bunch of toy blocks on the left side, and somebody asks, what size is the cylinder that is left of the brown metal thing that is left of the big sphere? Okay, so these are computer-generated questions that are easy to understand. So what happens is basically you take this sentence, you process it with an RNN, just like Mike basically showed you word by word. So these are basically a bunch of LSTMs processing this sentence and generating some vector representation for it. And then you have a convolutional network, like I showed you before, that processes the image, and then you basically split the output of the convolutional network into a bunch of objects, and then you take these objects and feed them one pair at a time to this function called G with the representation of the sentence as well. And then you take the output of G, add all these vectors that G produces, and then run another function F, which produces the answer. And this actually got 95 plus accuracy, human level accuracy on this one. So this is another model where having a static computational graph is a very difficult thing. Or thinking in terms of static computational graphs, but writing these things in terms of high-level computer language makes. Okay, so since I want to play with models like this, I wanted to have all of Julia be differential. So how do I do this? And how do I make it work fast? So you have to use GPUs for training these things, otherwise we take a long time. So so the first component is a Knet array that is similar to the GPU arrays that we talked about before. It's another GPU array type.
So just like the other GPU array types, you can actually initialize them giving dimensions. You can actually create one from an existing regular array, or you can take a Knet array, convert it to a regular array, both of which actually cause CPU transfers. And then to use these things in machine learning, let's say you have a bunch of arrays in W and a bunch of arrays in X, your model and data. These are regular CPU arrays, and this is how you train them, let's say. Now, all you have to do is basically map Knet array to these things. So this transfers everything to GPU. So I have a bunch of Knet arrays as my parameters and a bunch of Knet arrays as my data. And I can call the exact same function and the whole thing runs on the GPU. So from the user's perspective, they don't need to do anything special to work on the GPU except for using the Knet array type. In order to make this run fast, I had to do some tweaking. So, in particular, I did three things. One, I wrote a custom memory manager because the CUDA malloc is extremely slow. So what I do is, whatever pointers I get back from the Julia garbage collector, I don't actually release them. I reuse them. That gives me a lot of Okay, so when people think about differentiation,